Good evening, everyone, and thank you so much for giving this opportunity to present a paper titled as Rapid and Sensitive Electrochemical Detection of E. coli in Water using Chrome Gold Porosilicon, Porosilicon Sensor. So first, I will be discussing about basic introduction and the limitation of existing methods, then the objectives for this work, and then the experimental setup details and results, then readout of the sensor. So detection of E. coli is important as it can cause like waterborne illnesses such as gastrointestinal problem, diarrhea, nausea, and it can also like indicator of fecal contamination in water. The existing techniques for detection of E. coli are polymerase chain reaction, ELISA-based method, and membrane filtration, etc. So these methods generally use antibody antigen reactions, which makes them costlier and also have very complex procedure and requires like 20 to 24, 12 to 24 hours to give results. So to overcome these limitations, like we need a label-free method which can give a real-time detection of E. coli. So, for that, we have fabricated a sensor which is porous silicon based. So, first, in order to fabricate porous silicon, so first we have aluminum coated on the backside of the silicon wafer as shown in the figure, and then placed platinum wire and electrolyte solution in the etching cell. So here aluminum is working as a anode and platinum is working as a cathode. So by applying the current between anode and cathode, this etching of silicon wafer happens. So the optimized current density for this process is 9.7 milliampere per centimeter square, and time is 10 minutes. So after the porous silicon, the wafer was rinsed in DI water and dried in nitrogen. So followed that, chromium gold ID was made using thermal evaporation system. And to avoid the splices, we use PDMS O-ring, and the electrolyte solution will be dropcast in the PDMS O-ring. So due to this electrolyte solution, there will be change in electrical properties of this sensor. So we have measured change in potential between these two electrodes. So the fabricated sensor was characterized using FESM and Raman spectroscopy. So as shown in the figure, FESM image shows the porous network, which has pores around 20 nanometer, and the peak in Raman spectrum are at 519 centimeter inverse, shows the uh, con confirms the nanocrystalline structure of porous silicon. So the bacterial dilution was prepared using the secondary culture, which has OD equals to 1, by diluting it into DI and by using serial dilution process. So we have made 10 dilutions, and after that used H2O2 and kept it for 5 seconds to like for the reaction. So the sensing of the sensor is like depends in happens in two steps. So first step is a reaction of catalyst enzyme present in E. coli shell with H2O2. Then the reaction of remaining H2O2 on the surface of porosilicon. So the catalyst enzyme breakdowns the H2O2 into water and oxygen. And once we dropcast this electrolyte solution, the produced oxygen absorb on the surface of porosilicon and become reactives and further reacts with undecomposed H2O2 and releases charge carriers. So these charge carriers will move towards the terminals and we get the potential difference. So here figure A shows the response of the sensor for different E. coli dilution. As shown in the figure, the potential difference increases as the dilution increases, which means the remaining H2O2 solution also increases with the dilution. So the second step reaction will be more, so more potential difference. And figure B shows the calibration curve of the sensor. These E. coli dilutions further, the CFU in each E. coli dilution further measured on agar plate. And we have plotted this calibration curve. And figure C shows the response and recovery time of the sensor. So the response and recovery time both are in millisecond. Uh, we also performed this repeatability and stability of the sensor over 10 months, which shown in figure A, and also measured the response of the sensor in presence of DI, RO, tap water, and other bacteria, Pseudomonas and Citrobacter. So here this table shows the comparison of fabricated sensor with the previously reported sensor. So we haven't, like as seen in the table, we haven't used any antibody antigen, and it has very low response and recovery time, which is in milliseconds, and low limit of detection. This is the prototype of the sensor. So we have connected sensor with Arduino and LCD display. So here Arduino works as a to D converter and microcontroller. So it maps the change in potential due to E. coli dilution and displays the respective CFU per ml on the LCD display. So basically this works this work presents the application of porous silicon in electrochemical detection, and also gives the sensitivity around 113 millivolt per CFU per ml, and has the large detection range from 0 to 1.5 into 10 to the power 6 CFU. And uh, the chip-based prototype can be used for like rapid detection of E. coli. So this is the advantage as compared to the existing methods. So I would like to acknowledge Ministry of Education, Ministry of Jal Shakti and seed grant from IIT Jodhpur, and also the Department of Bioscience and Bioengineering for providing E. coli dilutions. These are the few references. Thank you.